A steel framework is used to support many types of structure. This often consists of vertical members, or columns, which transmit vertical loads to the ground, and horizontal members, or beams, which transfer imposed loads to the columns by flexural and shear actions. For beams, in-plane strength and stiffness are of primary importance in describing their response to loading. However, other actions may also occur, and this program will demonstrate the major physical phenomena that are involved in the response of unrestrained beams. Consider a model cantilever with a cross-section of relatively stocky proportions, subject to three distinct actions, which are vertical deflection, horizontal deflection, and twisting. Firstly, observe the response to a vertical load applied at the free end and through the centroid of the cross-section. The end moves downwards, with flexure occurring about the major axis. If a horizontal load is applied at the free end through the centroid of the cross-section, the cantilever responds by moving laterally. When the free end is subjected to a pure torque, the section twists without any translation of the centroid. It will be seen that, in general, all of these actions, vertical deflection, horizontal deflection, and twisting, can be involved in the response of a beam subject to loading which might be expected to cause flexure about its major axis. The next three tests all concern simply supported beams of varying slenderness. A central vertical load, causing bending, is increased to failure in each case. The first beam is just over a metre in length and can be described as being short and stocky. The load is applied to the beam by a screw jack device via a vertical rod. During the loading of this beam, here shown accelerated, deformations are confined principally to the vertical plane, with failure occurring essentially due to the attainment of a plastic hinge at the point of maximum moment. On removal of the load, permanent deformation remains. The second beam is 7 metres long and is much more slender. The load is applied as in the previous test. Observe the response, shown again in an accelerated manner. It can be seen that significant lateral deformation and twisting occur, in addition to the in-plane bending displacement. This is known as lateral torsional instability. The direction of the lateral movement is determined by the initial imperfections present in the unloaded beam. When the beam is unloaded, full recovery occurs, with the beam returning to its original undistorted shape. No permanent damage has been done to the beam, which demonstrates that the failure is elastic in nature and is due to instability. For the analytically straightforward case of a simply supported beam subject to a uniform moment m, using small deflection theory, the equation for the value of the critical moment MCR causing instability is as shown. EIY is the minor axis flexural rigidity, GJ is the torsional rigidity, and L is the length of the beam. Note the coupled nature of the lateral flexural and the torsional rigidities and the absence of major axis properties. For a very stocky beam, the plastic moment is significantly less than the critical moment, and instability does not occur. For a very slender beam, the reverse is true, and the beam will fail by elastic instability. The response of very stocky and very slender beams is quite clearly defined, and relatively simple to analyse, at least in an approximate manner. However, many practical unrestrained beams lie in the intermediate slenderness range, where the effects of elastic instability and plasticity interact. The third beam of this series of tests is just over 2 meters in length, and is neither very stocky nor slender. The beam is subject to load as before. It can be seen that lateral deformation and twisting occur, together with plasticity. Removal of the load is accompanied by only partial recovery of deflection, and significant permanent bending remains in both principal planes. Consider the following plot. The vertical axis is material bending strength, PB, in newtons per millimetre squared. The horizontal axis is lambda LT, which may be thought of as a lateral torsional slenderness. Clearly, for steel which has a design yield strength of 275 newton per millimetre squared, this value represents a limit beyond which the material may not be used whatever the slenderness. Conversely, whatever the material yield strength, the beam can still fail by lateral torsional instability. In terms of extreme fibre stress, this behaviour plots as a line which has a very low value when the slenderness is high, but has a very high value when the slenderness is low. This line, too, is an upper bound to the actual bending strength. For low slenderness material, strength is the limiting condition. But for intermediate values of lateral torsional slenderness, where plasticity and instability interact, the values of design strength represent a realistic, safe solution, with the reduced material bending strength being lower than the yield strength and also below the instability curve. There are other actions which are involved in the instability of beams. One of these is warping. For steel beams, actual warping deformations are very small and are barely visible, but they may be seen using the soft rubber model. This short beam is being subject to equal and opposite end couples, and torsion occurs. However, in addition to the primary twisting action, it can be seen that the end cross-sections no longer remain plane, but the elements of the cross-section distort out of the plane perpendicular to the longitudinal axis of the beam. This phenomenon is known as warping. In this example, warping is free to occur, and the equation for the critical moment given earlier is valid. However, if axial movement is restrained so that warping is prevented, as is often the case in practice, then this equation is modified by the addition of an extra term. The moment corresponding to instability is now enhanced by being multiplied by a factor which is always greater than or equal to 1. The warping component of the instability moment contains a term which is related to the warping resistance EIW and the torsional rigidity GJ of the beam. Note that when L is large, the term in the second square root tends to unity, showing that warping is only important for beams of modest length. This reflects the relative importance of warping. Observe the response of the two cantilever beams which are of equal length and which have nearly equal major axis flexural rigidities. The one on the left has a high minor axis stiffness, whilst the one on the right has a low minor axis stiffness. Initially, as equal load is applied to each beam, their behaviours are almost identical. However, for the beam with low minor axis stiffness, as loading progresses, instability intervenes. The cantilever on the left does not suffer any instability and would eventually fail by plastic action. Lateral torsional buckling is only likely when a section has significantly different values of second moment of area and is subjected to bending in the stronger plane. So far, little has been said about the end conditions of the beams. As with columns, the end conditions have a considerable influence on the stability of the member. This support is fully fixed and restrains all component distortions, whilst the one on the right is a simple support which permits rotations in both the vertical and the horizontal planes. This test shows two slender beams of identical cross-section. One is a cantilever. The second is twice as long and is tested as a simply supported beam. Load is applied to the cantilever and failure is due to instability. The simply supported beam is also loaded. Again, failure occurs due to instability. It can be seen that the distorted, buckled shape of the cantilever is approximately the same as either half length of the simply supported beam. Viewed from above, the out-of-plane deflections of the cantilever and either half length of the simply supported beam are obviously similar. This is analogous to the comparison between a pin-ended strut, corresponding to the simply supported beam, and a cantilever strut, corresponding to the cantilever. This correspondence is not exact, as the behavior of beams is more complex, as it also involves torsional effects. The end restraint provided to a beam has a major influence on the occurrence of instability and can be utilized to enhance the load carrying capacity whenever instability is likely to occur. An alternative way of increasing load carrying capacity is via the provision of bracing. Consider again a slender, simply supported beam. If it were unbraced, it would fail by instability, with buckling occurring over the total length of the beam. Bracing is introduced at the third points and attached to stiff framing. This bracing is in the form of light, flexible wires. Load is applied and, relative to the unbraced beam, the carrying capacity is considerably enhanced, as buckling can now only occur between braced points. On plan, the elastic horizontal distortions show that the effective length of the beam is reduced to 1/3 of its overall length. For example, the shape of the middle third is the same as the buckled shape for an unbraced, simply supported beam. This results in a corresponding increase in the critical moment. In this example, although the bracing is very light, it has considerable axial stiffness. This stiffness is important. If the support for the bracing is less stiff, then, whilst the strength of the bracing remains the same, the effective restraint has been significantly reduced. Load is applied. And instability now occurs at an intermediate load, higher than that for the unbraced system, but well below that of the system with a very stiff bracing. Often in structural situations, continuous bracing is provided to the compression flange. For example, by a floor slab which is carried by the beam. In such cases, the beams are prevented from moving laterally, and lateral torsional instability cannot occur. Bracing is most effective when restraining the compression flange, as it is essentially the compressive action in this region which causes the instability. In this building, the floor slabs are supported on shelf angles, a form of construction which provides good restraint. Similar considerations apply to bridge construction. Here, the longitudinal beams may be restrained on their upper surfaces. It is important to remember that, with a continuous beam supporting a floor slab or bridge deck, the slab will provide restraint in that region of the beam which is subject to a sagging moment. But, adjacent to the reactions, there will be regions subjected to hogging moments, where the lower flange is in compression, and bracing of this flange, too, may be necessary. One feature not mentioned so far is the level at which the load is applied. Consider a cantilever, such as one of those shown earlier, with the load applied through the centroid of the section. This may be regarded as the standard reference position. However, it can be seen that if the load is applied at the level of the top flange, then it exerts an additional overturning moment, which clearly enhances the torque and causes less favourable conditions. Conversely, if the load is applied at the level of the bottom flange, the resulting moment is tending to limit the twisting action of the section, which is advantageous in terms of elastic instability. Thus, the level of load application also has an influence on the behaviour of slender beams. Reviewing the major features demonstrated, it has been seen that the response of a beam to loads may involve three distinct deformation components: in-plane flexure, out-of-plane flexure, and twisting. This may also be accompanied by warping. For short beams, failure will be by plastic action. Very slender unrestrained beams will fail by pure elastic instability. For beams of intermediate slenderness, plasticity and instability will interact. Beam end conditions can significantly influence instability. Bracing can be used to prevent instability, but remember that bracing stiffness, as well as bracing strength, is important.